Okay, welcome back. So today we start now supersymmetry starts, and in some sense I don't even want to give motivation, but just a tiny little bit, so that anyway, just a tiny little bit. So originally, the introduction of supersymmetry, one could say, was motivated in particle physics. So this is what I learned when I took my supersymmetry course, something like 15 years ago. So the first argument was that if you look at the standard model, there is a naturalness or hierarchy problem. The second was that supersymmetry gives a very nice way to have the gauge coupling unification. And the third, even though we think we understand, the standard model is less than 5% of what we know for our universe. And there is the dark matter, which is a quarter of what is inside the universe. And I mean, in 81, Dimopoulos and Georgi proposed the minimal supersymmetric standard model as a model that, all at once solves everything. Of course, the minimal supersymmetric standard model, as well as close cousins of it, by now is excluded. But also because we had a little bit this discussion, actually after the Q&A session yesterday, I think it's very important to not forget, whenever your experimental friends or your pheno friends show you exclusion curves, they are for very specific models. Nobody at this day has excluded supersymmetry. Yes? So when people complain, you should tell them that this is a complaint about the current status of particle physics, that they cannot find anything. It's not your fault that you want to do supersymmetry. Yes? So that's it. That's the old school motivation. And I can say more without being recorded. But actually, the real reason why one should want to learn supersymmetry is if you want to understand quantum field theory, if you want to have any hope of understanding quantum field theory, you really need to study supersymmetry. And I will just say two tiny instances. I can make an insane list. So n equal to 1 super QCD can be studied beautifully. Like, we can actually understand what is going on because of supersymmetry. And very importantly, we can really plot the phase space as a function of the color and the flavor. And if you ask normal QCD people to do that, they will cry. They cannot do that. And another thing that you will have in the second and in the third lecture, the ADS-CFT. So ADS-CFT is one of the most beautiful things that we have in theoretical physics. It's really a shame not to understand it. And there is no ADS-CFT without understanding n equal to 4 super Young-Mills. In fact, n equal to 4 super Young-Mills, it's not too much to say that is a solvable gauge theory. This is a little bit of an oversell, but actually it's true. So, every day that is passing, someone is finding a new way to calculate the one little bit of an observable that was not known for this amazing theory. And in the large N is integrable. So you really want to learn supersymmetry, I think. And anyway, in the Q&A, we can say much more. I don't want to waste time. Now, so this is the motivation. But what I find very useful, I will do a very short history. Because especially in days of confusion, like where we are today, it's good to put your, like now you have seen physics for a few years, but when you see it for 10 or 20, when you grow up and be professors, you will really think in another way. So I started the history with the 60s, which were the era that really they were discovering a particle in the lab, and then they were telling to the theorists and things were happening. And you all learned in your particle physics class the Gell-Mann eightfold way. So basically the point is that they were finding hadrons. And these hadrons were organizing in SU3 flavor multiplets. So I will put this F there for flavor. So this is some global symmetry. Yes, and this was amazing, and people were ecstatic about this. But on the top of that, they were finding these SU3 multiplets, for different spins. So people were asking the question, can we actually combine? So spin is Lorentz, right? Can we combine Lorentz with some flavor symmetry? So they were asking. So that we have one big multiplet that has all the spins and all the flavor quantum numbers. And this is in response to that, Cole and Manuel Mandula in '67 and this is a famous theory that it's a shame I'm not going to prove because I have only a few hours to do this, but you should really look at the third volume of Weinberg. He has a super nice discussion there. So the answer of them was no, you cannot do that. And they proved the so-called no-go theorem. And what they did in that theorem, they showed that if you combine the flavor with Lorentz with a non-trivial commutator, your S matrix is going to be 0. So they should not be combined, basically. Having said that, and back then, by the way, there was no archive, which is very important, and there was a Cold War also. So I don't know what is worse. In '71, independently, without knowing about the work of the other people, and definitely also not knowing the Coleman Mandula, in back then Soviet Union, they found a way to write down an extension of the Poincare algebra that includes supersymmetry generators. I mean, they didn't call it supersymmetry back then, but there was a fermionic generator. And this was Goldfan and Lickman. And then again, also independently, the same year in the US and in France, there were two papers. There was the famous work of Ramon Never-Schwarz that you learn when you do string theory, and Cervin Sakita in France. And what they did is that they wrote down two de Lagrangians, okay, with what we call now supersymmetry. Some extra symmetry with a fermionic generator, yes? So they just did it. So whatever this theorem was saying was not good. It's just that people didn't know. And even more, and so these are the heroes of this class. We will write down, will be the first Lagrangian that we will write down. They wrote down a 4D Lagrangian with SUSY. Yes? So this thing, the fact that the Coleman Mandula is there, was addressed in '78 by Haag, okay, I should get, this is hard, because this is a Polish name, Zansky, and Sonius. Actually, Sonius has maybe the first supersymmetry review. I read it when I was a PhD student. It's actually super cool. You can try to look at it. So they basically generalized the Coleman-Mandula theorem to include supersymmetry generators, but then they showed that that's it. There is nothing else. Yes? So this is very important. So Again, it's really worth it to look at the third volume of Weinberg for these things. It's really nice. Fantastic. So now we really start. No more blah, 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 blah. Now we write. So first of all, the fermionic generators. First, I will write a schematic equation. They act on bosonic states, and they give fermionic states, and the other way around. We can say prime. So in the Coleman and Mandula and all the old physics, what we have been using is Lie algebras, right? So we have Ji, Jj equal to I, Jk, yes, things like this. And in order to be able to do this job, we generalize our Lie algebras to graded Lie algebras. I am clearly seeing that my letters are way worse than Andrea's letters, but I hope that they are still readable, yes? I'm just trying to write too fast, maybe, but it's okay, I think. So this is, so I'm introducing here something that is going to be called the fermion number. Yes? So F is going to be 1 for fermions and 0 for bosons. Yes? And if you do this, you win. You have your extended algebra with which you can play. And this is what they didn't take in account, Coleman and Mandula. Okay, so now I will more or less do a 2023 version of the paper, of the Russian paper. We will derive first the minimal SUSY algebra, and then we will go a little bit more crazy and get an extended version of that. Are there any questions? I started. Is it okay? Yes, please. That's amazing. I will not do this, but I am very happy to tell everything about conformal. Yes, I'm very happy to do that. Yes? Conformal, you have to be careful when you have conformal and scattering matrix. You have to be careful. You have to yeah, it's not, yeah. Very good. So first, so this is called n equal to 1. So this n calligraphic is the most important new notation. It counts the number of fermionic generators. And we'll introduce one guy and its complex conjugate. And that's it, and nothing else. Yes? And my job now, for the next little bit, will be to tell you what this algebra is. Okay. Of course, Poincaré is already done yesterday, so now I add these things on the top. I am writing empty things because I will derive all of these things, yes? Oops. And look here, I already made my mistake, but this is very nice. So when you have two fermions, you get an extra -1, so you get the curly bracket, yes? You get a plus, not a minus. And maybe I already write here a 0, because this is this theorem. Yes, I'm not gonna say anything further than that. If you have a flavor symmetry, it has to commute. Yes? So let's start with the first. Okay, so first of all, yesterday, so Q alpha will be a Weil spinor, the thing we learned yesterday. And, it's the fundamental of SL2C, as we said yesterday. And because of that, this is how it transforms. Yes? So now let's write it out. Yes? And because at this stage we care about studying the algebra, we take all of the parameters very small, and we will always keep linear order, yes? So this is 1. So we keep this equation. Now, on the top of that, Q alpha is an operator that acts on the Hilbert space. So it's not just that. And let's call this states psi. So this is the set of states psi, yes? And you may want to compute correlation functions with this guy in, but then this states psi under Lorentz will transform with some unitary transformation. It doesn't matter. Like this, where now L is an operator I have not committed to the representation. It is what it takes so that it will properly act on this, on psi, yes? Now, fantastic. But now, you can really think that you are computing correlation functions like this, like in your quantum mechanics class. And just because I want to be lazy, let's just say that we are computing one of them, like this. And let's transform under Lorentz. So I will put a prime. So one way is you transform the Hilbert space. Another way is you transform the operators, this passive versus active. So if this is what I am doing, I can also write this like this. Yes? So from this I learn that either I think that psi transforms or Q transforms to this. Under this guy that just wrote. Is everyone happy with this? Well, if you are happy, we have it. So what do? We just set the two equations equal, yes? And I didn't expand, but we expand also the second equation with omega mu nu L. And okay, you are big kids. You can do this calculation by yourself. Okay, I should maybe be a little bit careful. This is what you get. Yes, you only keep linear order. Yes? So we have the first entrance here. Oh, sorry, I'm horrible. Yes? And by the way, you can also dagger the same equation and write this guy here. Let me write up. Ooh, this is not nice here, but okay. Yes? So that's our first line. Now here. Maybe you can try to stop me from erasing this blackboard. I want to fill it in so that we don't write everything over and over again. I want to keep it until a lot. So now here. Okay, maybe I just delete this little thingy. How do we do this? No. Before I say how do we do this, I want to tell you another way of getting this. So what is another way of getting this? This is why I did this higher representation of SL2C yesterday. So Q alpha is this in terms of representation, yes? What is del mu nu? Is an yes. So this is, we insisted yesterday and we also talked about it with the Q&A. So you have a 6, which splits in 3 plus 3, 1, 0. Very good. So this is what this is. Yes, let's multiply. This is what we get. But what are we doing? We are doing a minimal extension of the Poincaré algebra, which means that the only generator we added is this guy and the bar. So this means we simply do not have this, and we simply do not have this. It's not in our original ansatz. So the answer is Q itself. And of course, with a little coefficient in the front, and of course, the precise number that you get in the front has to do a little bit with your notations. But in fact, just by knowing this, and just by a little bit matching the indices, you win. Yes? So you don't even need to do what I did. It's easier than that. Yes? So now for this, let's start with this logic. So I want to calculate something. What is the vector? Oh, maybe I should not write, maybe I should ask. Okay, now I did it. So let's do this multiplication. What do I get? Loud. Thank you. Do I have this guy? No. So this is the answer. And this is Q bar, yes? So what am I getting? I am getting that this Q alpha with P it has to look like this. Or maybe let's put it down so that I can match the indices nicely. So in order to make things work out, and let's put this up so that there is no clutter. No, it's nice. That's what I need. Yes? Sorry, what am I doing? No, it's good. Sorry, no. I want to not have everything all together. Yes, like this is perfect. So this is my guy, and the only thing I don't know is the overall coefficient. Yes, let's call it C. We will derive it. And also we can take the complex conjugate of this equation. Okay, maybe I should just look at my notes and not derive everything by scratch. So we just write this, and this is star, yes? And now let's so we will use Jacobi equations now, which basically are consistency equations of the algebra we are trying to derive. And in this case, I will use a Jacobi equation with 2 momenta and 1 q. Okay, I can start writing here. Yes, so I hope I did it right. I just rotated the generators like this. This is already very nice, this is 0. So I only need to think about these 2 guys, yes? If you see something wrong, tell me. So what happened? So let's plug in inside here our first equation. So P mu, comma, I plug in, I bring this out. I can bring out many things. Dot. And there is a minus sign. This is not very visible. Yes? It's very hard to see. Yes? Yes? Okay, now I use the conjugate one. I collect all the stuff. Indices. This is what I get. But this is not 0 by any way means. So this means that C has to be 0. So 0. And the same, of course, for Are there any questions or it's easy? I mean, I can say something with the, I mean, I have notes. Maybe people don't need to really write. I mean, maybe they have mistakes, but I could share. I don't know.
So you will put your notes?
Maybe secretly, not on the website. Maybe we can just email them. Because I'm sure there are mistakes. And maybe you can this way help me find, because I see people writing like crazy, and maybe this is, yeah. I mean, I go through the pain. Maybe this is enough. Okay, anyway, here there is 0. Is it okay? So I just checked the group theory. I put the indices nicely. Unknown coefficient, check Jacobi, got 0. Yes?
Just to be editing.
Yes, please.
So since you are, I mean, let's say back in the 70s, nobody knew about, I guess, graded Lie algebras. So you could say, okay, maybe grading Lie algebras, Jacobi.
By the way, I'm not sure if they didn't.
No, maybe.
Yes.
This is just to
Yes.
overemphasize. Maybe one could say, okay, maybe there are some crazy graded Lie
So,
algebras where Jacobi is violated.
So you see, but this is why I made the historical introduction, right? it was very important that these crazy Russians, they said, oh, let's extend the algebra, the normal algebra by a fermionic. Like, you have to be crazy to do this. And then these crazy people did something at the level of an algebra. There were some other crazy people that now they are the heroes of string theory, that they wrote down Lagrangians. And somehow this all came together.
But could you think of, having some violation of Jacobi?
No. So violation of Jacobi has to do with associativity. So actually, we are a really super baby. We are keeping, like, we are doing the most minimal thing in the history of the universe. It's very important. Yes, and this Jacobi that I wrote here is the most stupid Jacobi because I have only one fermion. In a second, I will write a Jacobi with two Q's, and there will be curly brackets. So that's the only generalization you get, curly instead of square bracket, nothing else.
In non-associative theory, you could have non-zero.
Yes. But, and by the way, I am playing with these things in my life. It's very, anyway, this is the minimal, yes. Yes, there is a question, yes.
So basically, what these equations tell us is that these supersymmetry generators do not transform when they are carried around in space-time. So
in terms of P mu? Yes, they don't care. Yes, they don't care. Yes. We are definitely in flat space-time.
And that doesn't change when we...
If you have torsion and crazy things, so no, the algebra is always the same, but then you have to very carefully, okay, I don't know if you will do this with Andrea. You can ask me to do supergravity for you. You have to learn how to couple spinors on gravity. And this is serious. But once you know this, you can do this. Yes? Are they, okay, we can ask Andrea in the end of his class. Yes, this is a serious question. I delete, yes? So what is the next entry? Is this, yes? Let's do it first, like this. Ask me if you have questions. Don't ask the person next to you. So let's do this, group theory. What is this? This is a scalar. Do we have any scalar? No. Out. By the way, in a second, we will do an extended version and we will have it. So remember this equation, yes? So, but for now, that's the only thing we have. What is this? L mu nu. Yes? So what are we writing? We have Q alpha, Q beta, equal unknown coefficient, sigma, whatever, mu nu, alpha beta. Yes, that's it. And with this unknown. Hey, let's do the same. Jacobi. Now we will do it for 2 Q's and 1 P. Yes, let's do it. So the only difference now when you do your Jacobi is when you have two fermions together, you have to remember to put the curly bracket. Yes, because there is an extra minus sign. But other than that, it works the same way. Oh, this is, so this is two fermions, but this bracket is square because it's boson with boson. Yes? Equal to 0. What is this and this? 0. What is this? 0. because it only comes here. In a second, we will make something non-trivial when we will go extended. But for now, it's just 0. So, I don't know, something else. 1/2, comma 0 times 0, comma 1/2. What is this? We did it yesterday, yes? It's the vector. So what is the vector? P mu. Yes? Okay, so with this coefficient, you can try as hard as you want. You will never be able to fix it. You can check whatever crazy things that come to your mind. So we fix. And okay, this is again the Bertolini convention. Other people have other things. Yeah, maybe I write, there is no way to fix it. Yeah, there is no way to fix it. Jacobi, whatever, you can go crazy, no way.
Is there some profound reason for this?
No, there's nothing. It's completely stupid. There is no way to fix it. I mean, we will talk about this in a moment. No, I would say that there is no reason. I would really say no. No, no profound, nothing. Okay, so let's write it. And the flavor symmetry is 0, yes? So we have our n equal to 1 minimal SUSY algebra. And I just need to say a tiny little bit more. And that is, let's look at this algebra. Okay, looks nice, but there is something else that I can say. It has an outer automorphism. Basically, what you said. What I think this is what you were pointing out. So if you look. If you multiply Q alpha nothing happens. In math, it's called outer automorphism. Yes? And in physics, this is called R-symmetry. Don't ask me why. It's a letter, I don't know. Some historical reason. Now, if I play the same game that I played when I made the first derivation, and think that this is how Q's transform under R-symmetry, but then I also think that R-symmetry acts on states with a unitary generator U. So there is a U R e to the I, of course there is a parameter, and then there is a generator, and this is what acts on states, right? I can play the same game I played in the very first derivation I did for the first equation. So I can equate this equal, yes? I can equate this and expand, yes? And I get And I think I want to write it directly here. I get this. Is it clear or I went too fast? Now I know that these things are more new than what was yesterday, so if I go fast, you should just stop me, yes? Is everyone happy? So what did we do? One more time. We asked, take Poincaré, do the minimal extension, which means you allow only for these babies and no one else. Q alpha, 1 Q alpha, 1 Q alpha dot. They have to be together because of CPT, but nothing else. This is the n equal to 1 supersymmetry algebra. And the only thing I used is Jacobi identities. I didn't use representation theory, yes, basic representation theory, and Jacobi. Are there any questions? So this is in some sense what the Russians did in a simplified, smoothened out version, 2023. So if there are no questions, let's go extended by making this blackboard. That's why I didn't want to delete. So there is a generalization with n and this is extended in the sense that I add an index to my Q's and an index to my Q bars that goes from 1 to n. That's what I do. And of course, I anticipate a little bit, and I already put the index up for Q and the index down for Q bar. I'm already thinking that this is a fundamental representation of something, and then, conjugate. But anyway, at this stage, I'm counting Q's. You can just forget about this up and down. Yes? So this is the extended thing, and how am I going to do it? Trivial. This equation, nothing happens, because L mu nu doesn't know anything about how many Q's. What about here? The same, nothing happens. I just add the index freely. What about this? Who cares? It's all 0 anyway. Yes? What about this? Here we have to be a little bit careful. I already said this. So I, J. So before, is it still there? Yes. Okay, this was lucky, I didn't plan it. So now, we can actually introduce a scalar. And why is this? So, I have this Levi-Civita alpha beta, I have it in my algebra. But now if on the top of my Q's I introduce this extra generator Z, which is now antisymmetric in IJ, antisymmetric times antisymmetric is symmetric. Curly bracket is symmetric, yes? So, okay, maybe I write here, if Zij is antisymmetric, this equation is consistent. So I can write it. And of course, you could also, by the way, repeat this calculation by having here a Cij with indices, whatever. This junk goes through identically, and this extra thing goes to 0 again. Yes? Now, for this to be okay, basically because of this, or, I mean, whatever, you can check, you should check all Jacobi identities. I will just write here. Not only Z is antisymmetric, there is a further requirement. This new object needs to commute basically with everything. What am I forgetting? With any Q or Q tilde, all 0. Okay, so first of all, let's make some preliminary comments. Just because, actually, they are more than comments. Some of these things will be theorems, but okay. Some important, yes, please. Yes, I'm sorry, actually, the minus is bullshit. So this is bullshit. What else? What else did I do? So this is basically this. This is what I'm writing here, at the level of the algebra. Yes? So we have a unitary matrix that transforms this guy and gives this up to a small parameter that is dropped, and the same here. Yes? And bar, always in these lectures, represents complex conjugation. Yes? Yes. Okay, so let's start. Okay, this is super nerdy, and maybe I could even skip it, but why not? So the Poincaré, we learned it had two Casimirs, right? The one was C1, which was P squared, which is M squared, yes? But there was the other one. There was this other one that was the W mu, the Pauli-Lubansky, yes? So this baby now is not anymore a Casimir. Basically, because it doesn't transform with Q, basically because Q does not transform with L mu nu. And if you remember, W had an L mu nu in it. Okay, but we can fix it, no problem. So first we can define a shift. This is always this is a standard supersymmetry trick. When your bosonic stuff doesn't work, you shift in this nice way. So you shift like this. Then you can define a 2-index object. That is your shifted baby together with momentum. And now this is the new Casimir. I'm not going to check it for you, but it's good, and most importantly, this new Casimir, yeah, I mean, both is true. Yes? Okay, now two more very important comments that are actually theorems. So the first theorem is that if we have a supersymmetric theory, Every state has to have positive energy. Okay, just right. Yes? Let's prove it. Very easy. So let's take a state psi in the Hilbert space. I need a bigger chalk. And what we do, we take this beautiful equation. This equation will do everything for us, and we plug it in a sandwich. Yes? And you can also put ij, they go along for the ride. I will be lazy, yes, and I will not put them. So this now gives the energy or the 4 vector, yes, the whole thing of the state, yes, of psi. Okay, good. So this is one very nice thing. Now, of course, let's recall that Q bar is Q dagger, yes? So this can also be written. Okay, and let me be horrible and drop the indices. You can put them, just go faster. So I open up the thing, and now I recognize what this is. Yes? So this is Q dagger on psi squared plus Q on psi squared. Yes? Oh, this is positive. Sum of squares, nice. Yes? Take this, take the trace over alpha alpha dot. You proved it. QED. Yes? Yes. Yes, so yes, this is good. Yes, positive. Yes? Yes. True. Yes? I mean, you really want to do that because otherwise you will start making things with negative. You don't want to do that. You want to have everything positive and nice. But okay, this is a very good point. Yes. Something else like this? Good. So this is my second point. And unless you break supersymmetry, whatever we will do in this life, it will all be positive, yes? This is extremely important. And another theorem. Theorem prime. So within a SUSY multiplet, the number of bosons have to be equal to the number of fermions. So this is the number of bosons, and this is the number of fermions. Yes? Let's prove it. This is true if and only if the energy is strictly bigger than 0. If it is equal to 0, you cannot make the statement. Yes? Yes, this is very important not to forget. Yes? Multiplets are always, yes, on cell. Yes. No, it always happens, basically. We will have everything. It's coming. Good, let's do it. So, to prove this theorem, we need to define a little extra gadget. So first I will define this baby, which is basically what we had before. We had the fermion number, but now it's just plus or minus. So it's +1 for bosons and -1 for fermions. Yes? And to prove our theorem, I will define what is called the Witten index, which is very important. So, trace over this operator, what it means is that you go in your multiplet and you sum over all the states, having this guy inserted in them. So I write explicitly. So this now is the state in a multiplet only. So this is what this is. And here psi is states, all states. Yes? This is what this means. Is this okay? And what I will now prove as an intermediate step is that this is 0. Maybe here. If I am going fast, please complain. It's not like yesterday that you knew everything. And maybe some of these things, they need to go slower to digest. Yes? Yes? So how do we do this? Okay, this is a trick. Okay, so first of all, I choose a fermion in my multiplet, and you should do the same calculation with a boson in your multiplet, yes? I am just lazy now, but you can do this. It's identical. So I will do half of the proof here. Yes, the other half you can do yourself. So I take this baby. If Q acts on the fermion in the multiplet, it will give a boson in the multiplet. Nothing stupid up to now, yes? Now, if I act with this guy on the boson, what do I get? Nothing, just the boson. But again, we are in this multiplet, so I can write my boson like Q on a fermion, yes? And not only I can do that, I can do another sneaky thing. I can imagine that here, this is again, you cannot not agree with this equation. Yes? So what am I learning? And again, I want you to do the same with the boson there, yes? So it doesn't matter how you started, it's the same stuff. So what did we learn? We learned that Q is 0 on the multiplet. That's what we learned. Yes? Did we learn it? Oh, but this is very nice. Because now I can play more with it. Just because I like it, because I know what I want to get. I will take a trace. I will take this baby, write it as it is. And just because I know what I want to get, I will multiply with an extra Q. Yes? And because this baby was 0, this also has to be 0. Are you happy with this equation? If you are happy, we are almost done. I expand the anti-commutator. Okay, I am very sorry I'm not putting indices, but it's faster for me, yes? And I will make them wrong anyway, and then you will have to fix it. It's okay. Yes, so this is what we have, and this is 0. Yes? What about using the cyclicity of the trace here? Let's use it. Ah, I didn't use it nicely. Oh, I will use it also there. So what is this? If I pull out the -1 to the f, this is our commutator sigma mu p mu, yes? Okay, whatever, 2 is, nobody cares because it's 0. P can also go out because it's a number. That's it. Yes? Please complain if it's unclear. So here, yes, I just used this equation. At this stage, these are just numbers. This is the eigenvalue of the momentum operator. It goes out as eigenvalue. This is just a little number, set of numbers. So I just have this. And this is what I defined here, yes? Here I am using one thing. I am using that Q's commute with P. Maybe I will write this down. So this means that everybody in the multiplet has the same energy. Yes? Equal to 0. From there, all psi's have the same energy and momentum, whatever, p mu, eigenvalue. Yes? So this is crucial. Is everyone happy now with this little clarification? Yes, please.
Isn't this step when the evidence fails is p equals 0?
So this is only with this, yes. So this is what I am about to say now. If the energy is positive, then this has to be 0. That's what I am about to say. So from here, I continue to here. If and this is the famous Witten index that Witten invented in order to count if there is supersymmetry or supersymmetry breaking, yes? So it is always 0 when there is supersymmetry because of all these beautiful things. And if it's broken, you get some number. Yes? So we just proved this now. I wrote here, I will now prove, and now I did. Yes? Okay. Okay, but then we are done now, because now the next step is stupid. Okay? So what is this? This trace -1f is this sum that I wrote there over all the states. Let's split it into 2 halves. One sum of all the boson, one sum of all the fermions. And this is equal to 0, yes? 0 equals to this, equals to this. Yeah, that's it. Sorry that there is the same notation for fermions and for the F fermion number. It's okay. I think it's clear, yes? So what is this? This is a plus. And this is the number of all the bosons. And what is this? This gives a minus. So minus NF. So this is 0. So NB equal NF. Proved. If this. If it's 0, I killed my equation here. I cannot learn anything, yes? Yes? This is very important because all these beautiful things that the modern children, including me, I include this superconformal index stuff, it starts with these basic things. Yes? You can ask me if you want in the Q&A. Good. Are we happy? Is it easy? Yes? If it is good, we will continue, we will do massless representations. Bam. Yes? Yes, let's do it. Oh, this chalk is not nice. Okay, massless. Yes. So let's do this. Okay, maybe just because I want to be super crazy nice, I will tell you as an intermediate step that if you take L12 QI alpha, yes? So I am evaluating the specific generator, yes? The R3, yes? This is minus 1/2, 1 minus 1, zeros, of course, yes? So I just tell you this, you can check it, and don't believe me, check. And this, what does this say? Is that if I write this a little bit slower, on Q, let's say plus, I have minus 1/2 Q plus, and Q minus. Yes? So, this is the helicity generator, yes? Okay, I will say this in a second, but this is a... So, Q plus lowers helicity, and Q minus raises. And you can do the same thingy quickly for yourself with the bar, and you will get the opposite signs. Do this. Yes, please. Okay. Is it okay? So I will take again our favorite equation. Yes? And now we'll plug in the reference frame. We do what Wigner said. Sorry, the rest frame. Yes? And what do you get? You get this. Or you can put it outside, whatever, sorry. Yes? Is this okay? What is very important? Okay, let's put it outside because this is littering my thought. There are 3 zeros and 1 1. Yes? Because of this beautiful choice. Yes? So what does this mean? This means that for massless states, effectively what happens is that the Q minuses on states, they are 0, basically. So the Q minuses, they will not contribute. They are called inactive, if you ask. They will not and the only baby who will do anything in this life is the Q plus. Yes? And of course, here there are also our indices. So I have all of n calligraphic of my Qs. So we have n calligraphic fermionic generators and their dagger. And with a slight rewriting, we see the algebra of n calligraphic fermionic oscillators. Yeah, harmonic oscillator, like harmonic oscillator, but for fermions. I just get rid of this 4 epsilon, and we have it. So define A plus yes? And what do we have? And A with A is equal to 0, the same as A dagger. And by the way, this equation is true because of the equation of QQ with a Z. But if we have Q minus is to 0, this Z is gone. Yes? So we have 0. So we have n calligraphic fermionic, like the equivalent of harmonic oscillator that you learn in the quantum mechanics class. And that's it and nothing else. And the way I define things, A lowers helicity by half, and A dagger raises. Yes? Okay, I'm worried that you are writing like crazy and you don't have enough time to pay attention. Is this okay? Ask me, ask me. No? No. You want to ask? It's okay. Okay, but don't be afraid, I'm nice. I think I am, I try. Okay, I continue, yes? So now we will make multiplets the way you always make multiplets. If I tell you to take as U2, to make as U2 multiplets, how do you make it? First, you define the highest weight state, yes? Or lowest weight if you are a mathematician, yes? So I will do the same. I will define a Clifford vacuum. Which is killed by, so this is the highest weight state or whatever, lowest weight state or whatever you want to call it, yes? And I will construct my multiplet by acting with a dagger. So I start with the vacuum. I act with 1A, dagger. So first thing to say is that lambda goes up by a half, the way things are defined, yes? But not only that, this state, by definition, it didn't have any arithmetic index. But now I acted with this A guy, so it's very important that I remember that it has an index now. It's in the fundamental representation of this arithmetic. Yes? And then I continue acting. Okay, so this is the easy part. Plus a half is equal to 1. But one other thing to be very important, these babies, they are fermions. They obey this. Yes? So what does this mean? Whatever survives here is antisymmetric in IJ. So I will label this like this. Yes? So this is because of this. Yes? Is this helping? A little star? It's antisymmetric. And continue, continue, continue. You act as many times as you like. I1, IK. This is a fully antisymmetrized gadget. Yeah, very important. Continue, continue, all the way to the fact that you used all of them, and you have n calligraphic of them. Yes? Are we happy? And look at me also. I didn't write anything here because I antisymmetrized all the numbers, so I got a singlet again. Let's count more nicely. Maybe this. Let's count here because we are cool. Oh, no, let's go slow. So how many states are these? N. How many states are these? Yes. Yes? How many states are these? Yes. Yes? And blah, 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 and choose n is 1. Nice. Okay, so what is the total number of states in the multiplet? Yes, very good. This is a magical identity. Yeah. Yes? And because we learned, they are all gone, but we learned them before, we learned our beautiful theorems, and we learned that the number of boson is equal to the number of fermions. So this is 2 to the n minus 1 bosons plus 2 to the n minus 1 fermions. Yes? So formally, by representation theory alone, that's what you get. Yes? Not bad, amazing. But now there is one physics bit that I want to add to this. When we really want to study a physical theory, so this is sort of a theorem, CPT, charge conjugation, parity, time reversal all together, this should be a symmetry of the thing, of the theory. So if we have here some state with helicity, I don't know, -3, the +3 should better be there, yes? So if it's not there, we will impose it. And the way we will talk about it, we will say, if the multiplet is not CPT complete, we will add CPT conjugate. Yes? So if we need to do that, the total number will be 2 to the n times 2, because everything doubles. Yes? If we need to do that. I mean, I can tell you very quickly, we always have to do it unless your multiplet is maximally symmetric. But we will just do this. And I will say this again when we do this. So are we happy with this stuff? So if we are happy now, I will go through multiplet by multiplet. We will construct all of, we will just write them out. First, I will do n equal to 1, n equal to 2, n equal to 3, n equal to 4, all of them. Yes? Let's go. And this is an extremely important thing, what I will do here, because now we will see what we can make in life. Yes, what is allowed and what is not allowed. So, n equal to 1 multiplets first. This is if you want to make the minimal supersymmetric standard model, you have to know this, yes? So let's start with our reference state, the Clifford vacuum. Let's just set lambda to 0. I will do this for different values. What do we get? We just look, there is only one generator. So we have a 0 state and a 1/2 state. Yes? Stupid. Is the CPT complete? No. Okay, with these things, I want a big no. So what do? we take another Clifford vacuum with minus lambda, which is minus that, and we fix it like that. So this is the full multiplet. Yes? Is it good? Everyone happy? What fields do you see here? And let's count degrees of freedom. So what is this? 2 degrees of freedom worth of scalar. What is this? Complex scalar. Sorry? No. There is something that's not clear. Don't be afraid, just ask. Because if you have a spin half going this way, yes, then you do a transformation and you get the minus a half. So if you want to have a real theory, you have to have both of them. Is it good? You can just make a picture for yourself. You choose your spin like this, you do a parity, boom, the other way. You can do with all of them, of course. Yes? So, good. So what do we have? We have 2 degrees of freedom worth of bosons, which is a complex scalar. Let's call it phi. And we have 2 degrees of freedom worth of fermion, which is a Weil on cell. Yes? We did this yesterday. And let's call this psi. So they are on cell, yes? We will make them off cell maybe tomorrow. Yes. Good. So this is the Wezumino multiplet. And this is the multiplet if you want to have a quark in your theory, you have it with a squark. Yes? So this is how you make matter in supersymmetric theories. So maybe yes, I write matter. N equal to 1 matter. Okay, amazing. Let's now do whatever, a half. What happens? I have a half, I act, I get 1. For the same reason, it's not CPT complete, even worse than before. So what is this now? What do I see? I see a Weil spinor like before on shell. And what else do I see? Say loud. Yes. Now I will call it lambda, lambda alpha. This is my gaugino. And 1 vector gauge boson, yes? Or on shell. A mu. So this is the gauge boson and this is the gaugino. And this is called the n equal to 1 vector multiplet. Yes? Let's see how many multiplets I can make in 15 minutes. Let's take lambda is equal to 1. Yeah, what do we have? We have 1 and 3/2. And we have to add okay, so we have a gauge boson. And we have another thingy that you don't know what it is, and I will not explain now what it is, but it's the gravitino on shell. Is there anyone going to do supergravity? Okay. If no one does supergravity, I have to explain this in a Q&A maybe. Yes, because otherwise it's very sad. And of course, this is called the Gravitino multiplet for the Gravitino, I just write it. It usually has two indices, one Weil and one. Yes? And okay, last but not least, super importantly, this is a supergravity multiplet. N equal to 1. Yes, there is a question. No? So 2 and minus 2 is the graviton. All of these multiplets that I made, they have 2 bosons plus 2 fermions, all of them. The graviton, you know, maybe in a very stupid way that it is 2 degrees of freedom, is these ellipses when they oscillate and there is one in this way and one in this way, yes? So the graviton you know from your gravitational waves. This gravitino, maybe I explain. Yes? Is it too fast or is it okay? Okay, if no one is complaining, no one is stopping me, I go n equal to 2, and let's see how far I can get. N equal to 2. Okay, let's start with a vector because this is easier. So what do we have? We have zero helicity, vacuum first. Now I, because it's n equal to 2, I goes from 1 to 2. So here we have a doublet. For the same reason as always, this is not CPT complete, so I add. By the way, here again, with the second action, I anti-symmetrize 1 and 2. This is epsilon ij, epsilon 1, 2 is one object, yes? So what do I have? I have one complex scalar. I have a doublet of gauginos. So 2 yes, and a nice gauge field. All nice and on shell. 4 bosons plus 4 fermions. Yes.
How do you know is SU2 R?
Yes, good. At this point, I don't care. I just care the fact that there is a doublet. There is nothing else in terms of information. So SU2 is enough. Yeah. Yes, but actually both of them are there. Yeah. Very good. So before I started with lambda 0, let's start. What do I get? Ooh, this looks like CPT complete for the first time. Is it? Tricky question for the audience. Yes, amazing. So this is not. Bravo. Okay, Sakura will be happy with you. So, two ways out of this life. I mean, first of all, there is the old way that I learned when I was a student, because we didn't know the second way in 2010 when I learned supersymmetry earlier, 2005, oh my God, I don't say years. So, way out. One, just add the CPT. I added with another color. I mean, it doesn't matter. This noise is very bad. So you just add it. And this is called the hypermultiplet. Yes? So I combine the two real scalars in these two doublets into a complex scalar. And then everyone is happy. We have a doublet of complex scalars. Yes? And two Weil spinors. So in my notation, Q, I, these are my, okay, I'm not gonna. So this is my doublet of complex scalars. I'm sorry, I am already using the same font. So when something is a generator, it's math frac. And when something is a field, it's normal. I'm sorry. And there are two Weil spinors, psi alpha, which are independent from each other. And if you wish, they can beautifully form a Dirac spinor. Yes? Who cares about supergravity? We delete. I mean, we care. So way out one is this. Way two, this is the modern way, 2009 Gaiotto. Add an extra SU2 index. And you can think of it either as flavor or color. Whoa. So if you add an extra index, you have an object Q, but now this is, I will use another letter, because this is real, yes? What she said, pseudo-real, but I add an extra guy that goes from 1 to 2. But this is pseudo-real times. Okay, I'm writing something stupid, I'm sorry, but this is what it is. Pseudo-real is real. All the minuses are gone. Yes? So this is a good, legitimate thing, and this has half of the degrees of freedom. So it has only this baby and only one psi with an index. And this is called half hyper. This is what I had to learn when I wrote my second paper, 2009, when these classes started coming out. So this is a good multiplet by itself. It's a good multiplet, like any other multiplet. Yes. I mean, the important thing about this, in some sense, we almost never really use it, other than when you want to write, in these classes, usually you want to have small building blocks out of which you can build everything. So basically, this is a good building block, basically. That's why it's good to define this. And it's a very legitimate supersymmetry multiplet, so we learn it. Comments. What is going on here? So there, up there, we wrote down the so-called n equal to 2 vector multiplet. I didn't write it, but it's clear. It's a multiplet that has n equal to 2 supersymmetry and a gauge field. I write it. Yes? So this is what I will write here is very important for when we will want to do Lagrangians and superspace. So an n equal to 2 vector multiplet, you can think of it as that it decomposes in two n equal to 1 multiplets, an n equal to 1 vector plus an n equal to 1 Uesumino. Yes? And an n equal to 2 hyper is equal to 2 n equal to 1 Uesumino multiplets. Yes? Okay, I have 2 or 3 minutes. So, in principle now, if I was very nice and slow, I will derive for you the n equal to 3 vector multiplet. And I would tell you that it has to become n equal to 4. Instead, I will just do n equal to 4 for you, and you can ask me to do this in the Q&A session. Yes? But this is one of the very important things. You see, in the third week, you will meet Iñaki, and he is the n equal to 3 guy. And yeah, anyway, we can discuss this. So let's do n equal to 4, n equal to 4. So start with -1. So now we are in n equal to 4 realm. So this index goes from 1 to 4. Yes? This, because in n equal to 4, there is, maybe I write like this. We have some type of state, fully antisymmetric. This is equivalent, what did I didn't write? L. So if this is the fundamental, if this is a 4, this is a 4 bar. Yes? In terms of representation theory. What is this? 4 by 4 antisymmetric? 6. So what do we have? We have a gauge field, 2 degrees of freedom with helicity 1 and -1. What do we have? We have Weil spinors. Yes, on cell. And what is here? 6 real scalars. This is the famous n equal to 4 super Young-Mills field content. Yeah, we stop. And okay, I'm not almost perfect. Yes?